The next talk, which is by Yuriy Chaban from Diamond, from eBIC. So Yuriy is one of the people running many of you who do collect data at Diamond will know that Yuriy is one of the people running the microscopes at eBIC. And he did his PhD in EM in Groningen, did postdocs at Scripps, Birkbeck, and then ICR Imperial College. And now in the last few years, he's been at eBIC and helping many of the members of the community to collect their data. So Yuriy, where are you? He's supposed to be.
I'm here.
There he is, good. Okay.
Yes, I'm sharing my screen now.
Yep, share your screen, good.
Can you hear me?
Yep.
Okay, thank you. Right, many thanks, Helen, and I would like to thank the organizers for making this event happen in such challenging circumstances. And with my first slide, I would like to remind that Diamond Light Source and eBIC are currently open for research directly relevant to COVID-19. And you can find link below if you'd like to access the proposal form or follow the link on Diamond main web page. Yesterday, Yunson gave a very nice eBIC update and shared our future plans. Today, I'm going to highlight the key new developments from the last year. We have installed K3 cameras on all our Titan cryo microscopes. With software upgrades to enable IFS data collection, we can now collect up to 500 movies per hour in K3 super resolution mode. With help of CCP-EM and Shores group from LMB, we have adopted Reliant AT pipeline for on-the-fly data processing. We are able to incorporate an efficient cryo particle picker developed by Torsten Wagner at Max Planck Institute. And we'll speak about this in more details later. We have now constantly running super user program. The super users are able to collect more than one data set per session. They can also choose from one load of up to 12 pre-clipped grids. And we will be supporting remote EPU access for super users. And I think this feature will be very useful due to travel disruption caused by COVID-19 pandemic. Chameleon, a blood-free picoliter rapid vitrification system, is now available for users. Access to Chameleon will be integrated into usual beamline access, but currently, if you're interested, please contact Dan Clare or Miriam Beckner from RFI. We have installed CETA-D camera on our Talos in preparation for micro-LED data collection. This camera allows electron diffraction data to be collected without need of beam stop, and we plan to offer micro-LED data in future. Also, I would like to stress that we offer now the feed milling cryo-AT beam lines, and my next slide is dedicated to this. So we have two modes of access, rapid access and standard access. With rapid access, you get 1 day feed milling session, and mill grids are supposed to be imaged elsewhere, but you can also combine it with back session if you give enough advance notice. The standard access will include 3 days of feed milling and 2 days of cryo-AT data collection. eBIC has a twin. This is eBIC for Industry platform, which offers proprietary commercial access to all models to all modes of data acquisition. The demand was so high that it attracted co-investment from Thermo Fisher Scientific. They have installed and maintained dedicated cryos G3I and Glacios, and also invested in staff who is working at Diamond. This enables eBIC for Industry to offer a full service pipeline from optimizing the freezing of liquid samples to model building and refinement. eBIC for Industry also offers challenging data collections like faceplate and tilted data acquisition using Latitude software. My next slide is about our integration of our integration with help of CCP-EM and Shores group of rely on it, and now we're running a script which helps us to set up crucial parameters for data analysis, and then other parameters automatically calculated from these presets. With integration of Crayola, our data particle picking is so efficient that we can often skip to declassification and data cleaning step and go directly to ab initio model building. In some cases, users try to still do select best classes and they got it wrong, so the model was heavily biased. When we integrated cryo, we noticed the problem, which I can try to show here. So the particles which it picked, it's similar to other particle picking softwares. They were influenced by a severe ice gradient on some micrographs. And because on some micrographs, majority of particles prefer thick ice, they were underpicked. So to address this problem, we teamed up with Mateusz Oleg, who is a joint PhD student between University of York and Diamond. Mateusz has developed an automated procedure for estimation and removal of ice gradient, which he called Icebreaker. In this procedure, a micrograph is low-pass filtered and divided into a number of patches. Then K-means clustering, so that the intensity is pixel intensity within each patch is averaged and then subjected to K-means clustering. Then these patches can be mapped back on the micrograph, and you can see here result of local contrast improvement, which is based on local adjustment of grayscales for every patch. And this seems to be great for particle picking with Crayola, as you can see here, but also we can use the coarser division of the micrograph to estimate the ice gradient. So how we can use this? Icebreaker offers new opportunities. For the first time, we can routinely assign to every particle relative ice thickness value within the dataset. We have used Reliant helical tube ID in our experiments, but I would like to use this opportunity to open a discussion. Shall Reliant provide users with place to put user-defined values, which later can be used for analysis and manipulation with data. So you can see here we can effectively sort particles within micrograph based on ice values, and I think in the long run this information can be useful for optimizing the fully automated data acquisition software, as we can target holes with best outcome. Also, you can see that Icebreaker helps to adjust the gradient and improves number of particles picked. This is good classes which we use. Oh, sorry. This shows classes which correspond to particles shown here. So with Icebreaker, we're able to select particles, more particles from all ice thicknesses. So how can we use this? What we can learn about our data sets with this method? So here you see that we split the data set of 20 as proteasome of the 3D refinement into 5 ice groups, and we plotted angular distribution between each group. So for demonstration purposes, we have relaxed the symmetry from D7 to C1 for the last round, and it had unintended and very interesting consequences. So we expected that particles will remain clustered as they are in group 2. However, in group 1, we see that particles drifted apart, and we think that's because the signal noise ratio in thick ice is much lower, and this particle just simply cannot be correctly identified. Another interesting consequence, another interesting observation is that the polar cloud, which corresponds to edge-on views, is shifting as we go to thinner and thinner ice, and that's especially well demonstrated in group 4 and 5. So we can easily explain this if we consider the influence of gradient of ice thickness or particle orientation. So particle with longest dimension would be the first to encounter the force of approaching air-water interface, and as our plot suggests, the force at reorient. Such particles' behavior would be a matter of concern, since air-water interface interaction can lead to particle penetration. Therefore, thinnest ice may not be always the best. Uh, so we started to do these experiments with aim to better to optimize particle selection. However, as you can see now with this ice gradient estimation, we can do the whole range of different things, which I think might be extremely useful in data analysis and sample optimization. Now I'm going to switch to another aspect of data analysis pipeline, which we would like to optimize for the sample with a relatively small structural variation. Current data analysis pipeline is straightforward and efficient. On the opposite hand of the spectrum is this. Great structural flexibility of macromolecular machines is necessary to perform vital function in the cell. But analysis of such data often turns into time-consuming nightmare, which requires intervention. So we have two questions. How can we possibly automate this? And if you look at this chart, you can notice that we require 3D classes in order to optimize our model and split and perform 3D classification to split them between different groups. So we ask the question, can we sort heterogeneity before we have a 3D model? The common line projection theorem states that two different two-dimensional projections of the same 3D object always have a one-dimensional line projection in common, as you can see here for model A. But can we play this in reverse? Can projections of different models be separated based on similarities and differences between common lines? So our year-end industry student, Donovan Webb, set to explore this question. So we used a model generated from PDB entry 6 GDG and split it into two and generated two phantom data sets with one subunit removed, as you can see here. Then we mixed this together and generated 2D projections from each model and mixed them together. We performed a Radon transform of every image and split this image into a single 1D projections of sinogram lines. And then we used statistical analysis and dimensional reduction in order to plot these lines. And what is interesting here that if you look at this cloud, which demonstrates how similar or dissimilar the sinogram lines are, the single lines from the same sinogram are stretched in the cloud. So cyan and yellow represents two different sinograms, and you can see that they stretch all across the cloud. So this picture shows just 5 sinograms from this cloud, and so we can now, using our prior knowledge that these lines come from single sinograms, we can use it to divide it into groups. So first we try to find the sinograms which are closest together. Then those which are further apart, and so on. We can continue until we split this cloud into only a few groups. So using this approach, we were able to divide our model dataset with 97% accuracy. The models assembled from every subset were noticeably better than the model from all particles together. So that is especially visible here. You can see this subunit is much better defined in subset B in subset A versus whole set C. So while this method is in early testing stages and merely proof of concept, we hope that if we can fully develop it, we can greatly simplify the pipeline for analysis of complicated heterogeneous data sets. So in this, using this method, we can separate data into individual subset before we enter the 3D model generation and further refinement, and hopefully that will help to streamline the process and more automate this. So with this, I would like to thank everybody involved in this project. I would like to thank Diamond Light Source for funding our research, which enabled us to do this. I would like to ask all Diamond support groups and people involved in this research, Matteo Scholler, Kevin Colton, Peijun Zhang, and Donovan Webb. Also, big thanks to CCP-EM for help with running image analysis and other aspects of eBIC. And my specific thanks to all eBIC users, Tom Official Scientific, and also for Mark Bashan for helpful discussion. And at the end, I would like to bring you to your attention that as we prepared to test our data, we looked to Implied for test data sets, and what we discovered that actually majority of users of eBIC do not really deposit the data, which greatly complicates our research and optimization of our tools. So my last slide, I would like to send a message to eBIC users. Please deposit your data to Implied. Thank you for your attention.
Okay, thank you, Yuriy. Again, quite a few questions have appeared. I'll try and pick through a few of them. So the first few are about Chameleon.
Yes.
How much you like it, and that's from Burak Kabasakal. And Rajiv Singh has asked a few things about Chameleon, and do you get a uniform distribution of protein, and can you control the ice thickness and so on? So can you say anything about that?
Yes, so with Chameleon, we have less biased distribution of views. That we can say. Controlling ice thickness can be optimized because in Chameleon you can actually estimate success of your injection as you prepare your grids. So normally within session people are able to get reliable results. But yes, sometimes ice is a little bit too thick, especially for small proteins.
Okay, so there was a question about rely on whether Icebreaker was implemented from Manali Ghosh, and there's an answer from Shoris Sheris on here, so I'll just read it out because I'm not sure if everybody sees it. A further integration of Reliant into CCP-EM will hopefully also provide more flexibility in star file metadata labels. Besides that, I note that Reliant 3.1 will maintain yet ignore user-defined labels, so Icebreaker could define its own. So I hope that.
Yeah, great. That will greatly help us. And yes, we would like to implement Icebreaker at least at eBIC as soon as possible, because that seems like a great additional piece of software.
Okay, now there's a few questions. Maybe we'll just finish off with a few questions about CLIC. So yes. Julia Z, who I think is Julia Zanetti, says CLIC require you to you input the number of classes.
No, we specifically design it in a way that it will not require a number of classes, but instead we would like to specify a measure of homogeneity of the class, which can be used to cut the tree at specific level. And the number itself is still we're working out how exactly to present it. But potentially, it could be both ways. You can specify number of classes, or you can specify homogeneity of the class.
Right. And Ligo Wang says, could we apply CLIC to individual particles instead of classes? I guess.
The first thing we're going to concentrate are classes because it alleviates a few issues. It is sensitive to signal-to-noise ratio. The precision of splitting the data goes down as signal-to-noise ratio increases, which is not surprising. So, and also classification would provide us with a tool to use minimal filtration for elimination of CTF artifacts. So this is why I think it's easier to, it is easier to optimize using classes in first term. However, we also learn a little bit more about our classification, and we see that potentially we can actually use the classification itself to separate particles into homogeneous groups, effectively doing 2D classification and then following on to 3D assignment within the program. But this is a little bit further field, let's say.
Okay, so we're running out of time, but I just wanted to follow. There's one last question on this topic from Takanori Nakane about CLIC also. Is separability better in 3D than in 2D because you can use more information in 3D. I don't know if you can give a brief answer to that.
Yes, that's a 3D analysis technique. Yes, obviously we have at the moment we actually need to test the best classification. It's still something we planning to do because we need reliable 2D classes, homogeneous enough, so it doesn't affect 3D analysis. But it still can functionally say unpick false positives because we're using information from whole sinogram rather than individual lines.
Okay, thanks very much, Yuriy.